Formation of images by spherical lenses. The lenses used in optical instruments, such as your eye, eyeglasses, cameras, and telescopes, are all made from transparent materials that refract light. They refract light in such a way that an image from the source of light is formed. Remember what an image is. It's where rays cross. The root equation for all lenses is Snell's law of refraction, and it follows a flowchart that is summarized as follows. The main law is Snell's law of refraction. Each lens has a characteristic. It has a focal length, how far the object is from the lens, and how far the image is from the lens. Remember, an image is formed when rays cross paths. So the way we form images is we do it either graphically or mathematically. The graphical approach is drawing a ray diagram or tracing. Mathematically, we find the focal length using the lens maker's equation. We could find the location of images from the thin lens equation, and we could find the magnification from this equation right here. Let's go over the overview for this chapter, or this section. I'm going to start with lens characteristics, which will tell us the types of lenses that we have. We want to go over the image characteristics. Then 3, we're going to start drawing ray diagrams to look at the formation of images, and then we're going to start tackling things mathematically. Or 4, we use the lens maker equation to calculate the focal length, and 5, we use the thin lens and the magnification equations to calculate details about the image. Lens characteristics. A lens is a transparent material that uses light coming from an object that is refracted at the curved surfaces of a lens and forms an image. Let's set up a picture of what we will be looking at. So we assume that we have an object that's on the left, and this object is the source of the light. Light always starts from the left and goes right. So then I have these parallel rays, and then it interacts with the lens, which is a transparent medium that refracts the light. So then you get some type of refraction, and where the rays cross, this location is where an image is formed. There are 2 types of lens, converging and diverging lens. Let's look at these guys now. A converging lens has incident light that is refracted through the lens, and the light converges to one point called the focal point, and it's always opposite of the object. So now what we want to do is that we want to form a converging lens using 2 prisms. With light starting from the left, you could see that the ray comes in, and then the prism essentially refracts it, and it bends it down towards the bottom of the page. Whereas the blue ray, in the opposite direction, bends this ray upwards. The point where they cross right here, this is called the focal point. Now, a very important piece of the lens here is this area right in here. This is where I want to focus on. In this course, we deal with the type of lens known as a thin lens. A thin lens means that the refractions of the lens is so small or thin that we can ignore this path. Picture-wise, I can't even tell that there's a refraction. So a thin lens is a curved surface, and we now draw this picture. A thin lens has light that's coming from the left to the right. As it goes through the thin lens, it's refracted and it converges to this focal point called F1. The distance from the middle of the lens to the focal point is called the focal length. This focal point is called the far focal point. However, it turns out that thin lenses have two focal points. Instead of light coming from the left to the right, I can also have light coming from the right to the left. If this happens, then you can see here that the rays will then be converged to the point f2, where it has this focal length f2 as well. For a thin lens, the focal lengths of the near and far focal points are equal. f1 is equal to f2. This means then, when I draw a lens, I must include focal lengths 1 and 2. These two focal lengths are reference points to understanding how an image is produced depending on the location of the object. Are images of a converging lens. The top image has 3 rays that converge, whereas the bottom green image shows that you have an infinite number of rays that are converging to a point. In a very analogous way, I'm going to do the same thing for a diverging lens. I'm going to model the diverging lens using prisms again. As the incident light comes in from the left, the upside down prisms diverge light away. Now, if we were to follow these rays backwards, it appears that the light is coming from a single point. This would be the note that this near focal point is on the same side as the object. If I reverse the light direction, that means going from the right to the left, I have this situation. So by looking at this, you could see that there are now 2 focal points for a diverging lens. Now if we smooth this out and make it thin, this is what it looks like. So rays coming in, you see here that they have 2 focal points, the near one and the far one. Let's summarize these details. Converging lenses have focal points on the opposite side of the object, while diverging lenses has it on the same side as the object. Only parallel rays to the central axis cross at the focal point. No exceptions. Each lens has 2 focal points, the near one and the far one, and they have the same value. f1 is equal to f2. Each spherical lens has a curvature. This curvature is twice the focal length. Last but not least, a converging lens is thicker in the middle, while a diverging lens is thinner in the middle. That's how you can tell the difference between the two. When light goes through these lenses, they will form images. Next, we look at image characteristics. All lenses form images, and these images have 3 characteristics. 1. Image type, real or virtual. Real images are formed on the opposite side of the object, and it can be captured or projected onto a screen. There is actual light at this location where the rays cross. Virtual images are formed on the same side of the object and cannot be projected onto a screen. There is no light at this location, but our eyes are led to believe that light originates from this location. The second image characteristic is orientation. An image is either erect or inverted. If an image is erect or upright, then it stands above the central axis. If an image is inverted, then it points down below the central axis. All real images are inverted. All virtual images are upright. Characteristic 3. The image size. The image size is either smaller, the same, or larger than the object that created it. Picture-wise, I draw it the following way. So on the left here, I have the object, and its height is h object. In the middle here is the lens. So if I was to look at the image on the other side, then the image could be smaller, could be the same size, or it could be larger. The way we measure that is the ratio of the image to the object. The image size is measured relative to the object height. In other words, the ratio of the image height divided by the object is defined as the magnitude of the magnification, which we write like this. So then by looking at the value of m, we have this. If the magnification is less than 1, we say it's smaller. If the magnification is 1, it's the same. And if the magnification is greater than 1, then the image size is larger. The last image characteristic is the object and image locations. Object and image locations. The sign convention. There are 4 regions that classify the object and image locations. These 4 are relative to the focal point f and twice the focal point. Let's draw a picture of this. What you see here is that I have a lens, and then since the near and far focal points have the same values, I just label them as f. Now if you look at f, this is twice of f, and therefore I have symmetry between these 2 points here. The sign convention is if I have an image opposite of the object, it's always on the right side of the lens. That space is called positive for images. In red here, you see that the right side for images is positive. In other words, S prime is equal to the image location is going to be greater than 0. If an image is on the left side, the same side as the object, that image is negative, and it's a virtual image. The left side for images is negative, and therefore S prime, its image location, is negative if it shows up there. For a single lens, the object is always on the left and is defined as positive. Now that we established the sign convention for images and objects, I now want to go in and look at the image locations. An image on the right side of the lens is always a real image, and all of these images will have a location that's outside of f. These values are positive and these images are inverted. On the other hand, if I have a virtual image, it's going to be on the same side as the object, and these images will always be erect and their numerical values are negative values.